Thank you. Good afternoon, everyone. Welcome to the AstroAI Lunch Talk. Today, it is my pleasure to introduce Bonny Wang, who's visiting from Pittsburgh today and tomorrow. And Bonny is currently a master's student at Carnegie Mellon University. Her background is actually interesting. She's interested in cosmology and machine learning for cosmology, but she's also interested in entertainment technology. So she's been thinking in terms of building video games. So if anyone's into video games here, there's more to talk about, more than just AI. So she's a master's student, as I mentioned. She spent time as a researcher at the Flatiron Institute, working with some familiar names here that we see on the screen. And today, she's also spent time at the Kable Institute in Tokyo. And today, she's going to be telling us about machine learning cosmology for cosmic voice. So, Bonny, the floor is yours. Thanks so much.
Cool. Thank you.
I will just remind the audience, feel free to interrupt with questions. It's very open-ended discussion, so please feel free to ask.
Thank you for the very nice introduction. So I'll start with my talk about machine learning cosmology from cosmic voice. So this is a brief outline of what I'm going to talk about. First, I'll introduce what are cosmic voice in case people are not familiar with, and then I'll talk about how to constrain cosmology directly with void properties, and also constrain cosmology with void galaxies. So some of the background information here. So what are cosmic voids? So if we look at our universe at very large scale, you'll see these cosmic web structures. There's like dense regions like clusters and filaments, and voids are those like very underdense regions, contains like very few matters and mostly their energy. And on the left, this is like a simulated cosmic web, and this is what we observed from the SDSS survey.
Can you put your microphone a little bit closer to you?
Oh.
Or try to speak towards it because it's
okay.
We're losing you a little bit. Yeah.
Why do we want to study cosmic voice? So cosmic voice is actually a very novel way to do dimension reduction on cosmological data. Because usually when we have the galaxy distributions from surveys, traditionally people use two-point statistics or power spectrums to do cosmological inference.
Sorry.
Right.
You got a filter on your Zoom. Where did Zoom go?
So video filters?
Yeah.
Videos to the arrow there.
Where is that setting? Does anyone know how to turn off the? It's a mustache filter. Backgrounds. Wait, sorry, where? There we go. Video filters.
Just for those interested, that's my son playing with my Zoom, so apologies.
There we go.
Oh, that's so funny. Okay. Yeah, I was wondering.
You don't mind hearing yourself with a mustache.
Sorry about that.
Yeah, I was wondering why I look a bit different.
Alright, let's go. Alright. There.
I'll keep talking. Alright, that was hilarious. But anyway, so traditionally people will use two-point statistics or like power spectrums to do cosmological inference. But if the distribution is beyond Gaussian, then you need to capture the more non-Gaussianity in this distribution, you need higher order statistics. And voice is a way we can extract information from these distribution and capture the higher order statistics. And voice is sensitive to structure growth, dark energy, modified gravity, sum of neutrino masses, and galaxy formation. And there have been some very good constraints from voice with the Bohr surveys. For example, if we look at the void galaxy correlation function, we're able to constrain omega matter to 5% error. And if we use void size function, we're able to constrain both omega matter and sigma 8 to pretty good precision. So now I'll talk about first my work on extracting cosmological information directly from void properties. So the problem we're seeing here is our universe will look quite different if the cosmological parameter have a different value. So if you see these three pictures have different values of omega matter, and so the problem we're dealing here is, so we have our observation for our universe, and we want to, from our observation, we want to know what's the values of cosmological parameters. And specifically, we want to know if we use the void data and how we can link them to cosmological information. So this problem is not easy because it contains it's very high dimensional, and we only have one real universe. So we solve this by using machine learning for high dimensional problems and simulations, so that we have data to train our model and not only dealing with one real universe. And this is a bit technical. So this is an algorithm we use to find voids in the galaxy distributions. We use Voronoi cell tessellations and watershed transform. So basically, we have this map of galaxy distributions, and we run the Voronoi cell tessellations. And if you notice, the volume of the Voronoi cells is the inverse to the density of the region. So so these volumes are approximate estimation for the local density of where these galaxies live in. And after creating these Voronoi cells, we set a threshold to the density, and we start from the local minimum and keep merging the cells adjacent so that the density reaches the threshold, and we identify this region as void. So if you notice, on the edge of the voids, we have smaller Voronoi cells, meaning they're more dense regions.
So this is you're applying this to simulated data from the simulations, and then the center of each Voronoi cell here corresponds to what in the simulation?
So usually they correspond to galaxies, or sometimes we can also run it on different particles, like halo particles, but this work is mostly on just halo or galaxies.
So each point is a galaxy?
Yeah. And this is just a show to how the galaxy distribution and Voronoi cell in 3D, because our data is actually in 3D, but it's easier to explain in the previous 2D image. And the void property we're focusing here are void elasticity and void density contrast, because there's more to explore for these two properties, and combined with void size, they kind of characterize each void size, how big is voids, and elasticity, how they differ from the spherical assumption. And void density contrast is a value that defines how deep the void is. So basically, it's the ratio between the density on the edge of the voids and the minimum density inside of the voids. And this is just some visualizations to show how different voids with different elasticity will look like. This is one of the advantage of the void finding algorithm, because we can have the shape information of voids, while some of the others mostly assume voids are just sphere. And this is voids with different density contrast. So the wireframes are the Barnell cells, and then the points are galaxies inside. So we apply two kinds of machine learning architectures in this work. One is just a very simple fully connect layers, and the second is using deep sets on void catalogs. I'll talk about this more in detail. And the last function we use here is from moment networks. So using moment networks, we can not only get the mean value of the posterior distribution, but also like further moments for the distribution. So here we predict up to the first moment, and the second. So we both have predictions on the mean value and also the standard deviation or the variance. And this is the overview of the first architecture. We just input the histograms of void elasticity or the void density contrast, and we put constraints on the cosmological parameter, both the mean and standard deviation. And this is results from the first model. So if we use only the histogram of void elasticity, we're able to constrain omega matter. And if we use the void density information, we're able to constrain both omega matter and sigma the fluctuation. And so if you see here, the x-axis is the true value, and y-axis is inference, and the middle line here is where the true value perfectly match the inference. And each point here is the mean value prediction from the machine learning model, and the arrow bars are the standard deviation from the machine learning model. And you can see most of the points and arrow bars kind of touch this perfect line where the true value matches the inference. So we're confident to say they have constraining powers to these parameters. And there's also some statistics. So the chi-square is kind of closer to 1, and the R-square is close to 1 within reasonable values, and the root mean square values and relative errors are all within good values.
Sorry, can I interrupt again? How do you estimate those error bars from the machine learning model? Is your neural network Bayesian in some sort of, or how are you actually estimating your error bars here?
So actually, we use this loss function. So this is how we kind of like, so you have the f function and g function. They're both like modeled by the multi-layer perception. So there are just basically two output nodes from the machine learning model. And then the first part of this loss function is like a mean square error. So it basically minimizes the difference between the mean value and the true value. And the second, so this is the predict variance, and this is this output, we assume it to be the variance. So we kind of minimize this term so that we also minimize the difference between the predicted variance and the actual variance between our prediction and the true value. Hopefully this answers your question.
I'll ask you more details later. I'm not sure I followed.
Cool. Yeah, and secondly, we also use deep sets because we think this architecture is particularly suitable for our data because we have a set-based catalog. And deep sets is a kind of machine learning model that's a simplified version of graph neural networks, if anyone is like familiar with graph neural networks. So basically, deep sets have each node, and also, so each node will be a void, and they have some node features like the void size and void elasticity and void density contrast. And we have two multi-layer networks here. So the first one will keep we keep inputting each node or each void's information, including the size, elasticity, and density contrast to push them to a higher dimensional space. And we keep applying this multi-layer perceptron networks to all the voids in our catalog. And so that we kind of have these updated node features and like more higher dimensional void features. And then we use operation invariant. It's like the pooling operation here, so that we calculate all the void property in higher dimension and do some min, max, and min values of all the latent features, and then input them to a second multi-layer perceptron, fully connected layers, and then we have the final prediction on the mean and standard deviation for the cosmological parameters. And this is the result. As we expected, we get better constraints with using only like one void properties, and also like using histograms which have information losses as the input. This way we can directly apply all the information we have to the deep set, so that we have less information loss from this architecture. So these parts are have the same setup as before, and we can see we're able to constrain 3 cosmological parameters, spectral index as in addition, and they're much closer to the like the reference line, and the error bars are smaller, indicating there are more have better constraining powers on those parameters. And you might notice the chi-square value is a bit higher. This is mostly because we have some extreme values with very small error bars, which drive this value a bit higher. But if we remove them, they're mostly within reasonable ranges. And next, I'll talk about additional work. So besides constraining cosmology directly from void properties, we can also constrain cosmology with void galaxies. So the setup here is, so we have the galaxy properties within a void, and we put them into machine learning models. Here is just very simple neural networks, and we are able, we want to do predictions on the matter density parameter. This work is a subsequent work from the cosmology from One Galaxy paper. So from the previous work, they basically saying like, if we use machine learning, we can directly put constraints on matter density parameter with the property of one galaxy. So this property including the radius, the metallicity, velocity of the properties. And this work have been not have some subsequent work to prove these trees, like we can also extend to multiple galaxies, and there's robustness tests. If we train the machine learning model on one simulation, then we're also able to do predictions on the simulation data from another simulation with the different galaxy formation models. So this adds some more robustness to this test. And there's also tests on photometry data instead of like just simulated galaxy properties. And however, in this previous work, they're just choosing random galaxies. And we want to know if we are going to actually use this method to do constraint, like should we be biased on galaxy selections? And then in this work, we propose we want to use void galaxies specifically. And some background information on void galaxies. This is still a very active discussion field And there's lots of research on how void galaxies differ from traditional galaxy in the denser regions, and whether they have lots of difference or they're the same. But usually we expect them to be bluer with lower mass and higher star formation rates. And we assume they're less influenced by external disturbance such as stripping and harassment, because void galaxies are in a very isolated environment where there's no like lots of like disturbance from like clusters or other nearby galaxies. And the environments in voids are closer to the early universe, where there's no lots of like structures formed. And we think they could have stronger connections to cosmology and the physics of the early universe. And the data set we use is from the Cannon simulations and using the illustrious TNG set, which they sampled in a Larkin hypercube way. They sampled the matter density from 0.1 to 0.5. And how do we select void galaxies? So we kind of want to make sure that the galaxies are actually like quite isolated as we expected. So we use both the void position, so to make sure the galaxy in the large cell structure, they're in less dense regions, and also the Borneo cell volumes, so so that they're more isolated in the local environment, because Borneo cell volume, if the larger the cell is, the void galaxy is more isolated. And we also perform some additional cuts to see if we put more constraints, if we make select the galaxy to be more isolated, if we can get better constraints on matter density parameter, which is our assumption. And we perform both the void core density and void radius cuts to our dataset. And this is results we have. So on the left column, we have the non-void galaxies. The middle is the random galaxy. On the right is the void galaxies. And so we have the true values and the inference values, and also the reference line where the true meet the predict values. And we can sort of see that from non-void galaxies to void galaxies, the points are closer to the void reference line. And we also have the statistics from R-squared have like about 5% improvements from the previous random or non-void galaxies. And the root mean square values and relative errors also improved from other types of galaxies. And from top to bottom panels, we actually increase the threshold for the Vernal cell threshold for selecting void galaxies. So in the bottom panel, we have more isolated galaxies. And you can see the statistics also have more improvements on our root mean square error and also relative errors, and the points are also closer to the visual lines with smaller error bars.
So, so basically, is what you're telling us that that isolated void galaxies are more sensitive than cosmology than galaxies that are not sort of in the surfaces of those voids, I guess, are less isolated. Does that mean that regardless of the cosmology, there tends to be a tendency of, cosmological evolution for galaxies that actually live in more clustered environments to get more homogeneous in their properties? Is that what's happening? So for those galaxies, any interactions and stripping and all that would make the cosmology less relevant to how they look today? Is that what this means?
Wait, can you repeat?
Sorry, maybe I'm just thinking out loud here. So galaxies that are isolated are more sensitive to cosmology. The question is why?
So we think it's mostly because the environments in voids, there's like less matters and less structures. So these galaxies are also like, from observation, they are usually younger. So they're actually, even though we observe void galaxies at redshift 0, they're actually resembles galaxy that's like at like high redshift or closer to the early universe. So they might carry more information, and they're also in a very like isolated environments where the physics are mostly now, and there's like less disturbance from others, so they're more like closer to like a idealized galaxy, and they might carry more, they're more sensitive to cosmology.
And then just to follow up quickly, so how common are those void galaxies in simulations, and how common are they in observations?
So first this depends on how you define void galaxies. There's no like very robust definitions, and also depends on your void finding algorithm. But in our method, if you see here, this is like if we have like a loose threshold, then it's like 0.1 or 0.2% of the total galaxy distribution. If we increase the limits, then it's only like 0.03% of the galaxies. There have been some observed void galaxies. I'm not entirely sure about their percentage in all the total galaxy distribution because there haven't been many, but I don't have the number right on top. Yes.
Yes, sorry. Very wonderful. So it's kind of related to the question that they asked. So in TNG simulations, one way to potentially identify voids, and please correct me if that's not your method, I think is actually going to either the subhalos or groups and look for low density environments. So if you, and I mean, again, I don't really know the details of your work, maybe that's what you have done or maybe not, but I can imagine that you could just identify groups that their actually average density is like lower than the, expected ones for a typical mass of the actually hello group. And then if the group is actually relatively low density, there is more chance that the members of the group or subhalos there that are also lower density. Is this the method that you used, or is it a different one?
I think like yes, we are using like the subhalos, which illustrates TNG considered as galaxies in this simulation, and then we run the Vernal cell finding algorithm on those galaxy distributions.
Okay, and then so the follow-up question is that what is your criteria for average density, that if you're below that, you just call them low density or void?
You mean like when we perform
like when you filter out, I mean, you said that less than like 0.03% of those like a total population are identified as void. That definitely also depends on your threshold that you use for identification of them. So something that will be really cool, again, I don't know the details, but that could be potentially that you just change that threshold and see whether there is any convergence of the behavior that you're seeing here. Because the fact is that sometimes you may have very small sample and you might be overfitting basically. I mean, that just like going completely in the diagonal part, it just worries me slightly. So seeing the transition from very low density to higher density, maybe that would actually tell us where we are.
Yeah, I think like one thing I want to clarify, and sorry for not clarifying before, is that like when we train the machine learning model, we actually use all the galaxies in the simulation, not only void galaxies. So it's like after the machine learning model is trained, we select the void galaxy to see their predictions. So the overfitting problems it will not be affected if we are using like the void galaxy have like much less numbers, because like when we train the machine learning model, we kind of want to make sure it have seen all the different types of galaxy and able to predict. Does that help with your question?
But still, your training data set for voice wouldn't be enough, right? Like, I can imagine when you have these different, when you have these different populations, right? So on the right, you're just considering void galaxies, right? So you can't use the data which are trained for all galaxies. You have to go to a subpopulation of them that are called void. Maybe we can discuss later. But the other side that is no void or random galaxies, I imagine for random galaxies you can use all the data. But for void galaxies, you have to remain on the subcategory that is called void. And if this is not representative, I don't know, maybe, I'm sure you were very careful about this. I'm just like not really sure about the details.
Yeah, that's actually a very good question. So this work here is mostly to see, like, we have the machine learning model, we train it on all the galaxies so that if we see one galaxy, it's able to predict the cosmological parameters. And because we have this frameworks which maps between one galaxy property and the matter density parameter, we want to see if we select void galaxies to these already trained models, whether they have better error bars and closer to the true value of cosmological
I see.
parameter.
Okay, good. Yeah.
Thank you. And this is additional tasks we make because we think like having more isolated galaxy will lead to like better constraints on the matter density parameter. So we are trying different ways to be more selective on the void galaxies. So we perform, this is when we only do the core density cut, and then on the right we have perform additional radius cuts so that we are actually selecting the very void, very large void, because sometimes there will be like fake voids in our data set because of our algorithm and the resolution of the simulation. So we want to make sure the voids we are extracting are actually the actual voids in our data. So we also, so this is from left right, we are being more restricted on void selection, and we can see like if we become more restricted on void galaxy, we can also see the improvement on the statistics, which is consistent with our assumption. So for this part, it's from 0.79 to 797. Sorry, from 96 to 97, and all the statistics also improves if we becoming more restricted on the void galaxy selection. And this is also a plot for the Voronoi cell volume and size of the error bar. So if we have like larger Voronoi cells, meaning the void galaxies are more isolated, we can have like smaller error bars, like so that the more isolated void galaxy can have better constraints on the matter density parameter. Okay, and this is my summary. And in addition, I want to say, like, while there is like very trendy to like use very complex models on lots of different problems, like my works also like focus on applying very small models to very well-defined problems, and finding the problems that's like very suitable for just like machine learning methods. So I just want to briefly mention some of my other works. This is actually a work on asteroids, and so this is a paper, a collaborative work which is just recently accepted by Nature Astronomy. So basically, there's observed gap between asteroids' rotation frequency and also the size of the asteroids, and there's a gap from the observation that we could not explain previously. And then basically this paper proposed a new theoretical model for explaining why this gap appeared. And this is the simulation from the new model, and you can see it kind of like replicate the gaps in the observation data. And my work is mostly trying to find the location of the gap from a statistical view and then compare with a theoretical model. And so this is, we use semi-supervised machine learning and to identify where the gap is. And fortunately, it's like quite consistent with theoretical value. And I'm also in the DREAMS project. We're doing some machine learning from halo structures to predict quantum dark matter mass. So, and also some cluster mass prediction. So if you're interested, stay tuned or talk to me later. And also I want to quickly mention, I also do some scientific visualizations and outreach because I feel like my journey to Astro happens a bit late in my life, so I want to make like scientific research become like more accessible to more people and making them more fun. One of my mixed reality project about cosmic voids is actually mentioned in the Scientific American. Quite proud about it. And I also built a VR game about lunar exploration and help a local museum to get secure the NASA grant for STEM education. This is some just like visualization I did for different projects. There's Floyd, large scale structure, asteroid approaching white dwarf, and asteroids. And something like making things more fun. This is an image of Paco. Not sure how many people know him. Here, this is generated by normalizing flow, actually. So this is like a machine learning generated Paco. And also I like putting some like data in. Oh, it's not changing. Never mind. It's
You might just need to press it with the cursor.
Okay. Yes. This is just like a crystal cube I built for the Astro simulation at CMU. I think it's quite worth to putting them into an interesting way because we spend so much time on our simulations. And as a researcher, we actually know like how amazing these structures are formulated. While like some people don't know, like my mom, she said like, why you're putting dust in your cube. And this is like a recent started project on GitHub. So I'm posting some visualization methods using 3D softwares to help